Okay, I'm back. So, yeah, I've consulted some colleagues, and it looks like what I'll be doing here is just recording probably 15-minute clips, since I can't pause the recording, which seems really ridiculous to me, but that's where we are. So, anyway, I'll record 10 to 15-minute clips, and then upload them, and files won't be so big then as well. So maybe that's a blessing in disguise. So we last left off with looking at the gyromagnetic ratio, looking at the units on the angular momentum, which then mean that the units of the moment are going to be in terms of the Bohr magneton, which is where I left off. And so the Bohr magneton is usually designated as a mu subscript b, or sometimes as a beta. Okay, so the Bohr magneton can be designated as a mu sub b or a beta. Your text uses mu sub b, so we'll stick with that designation for now. So for the electron, if we were to actually do that calculation, mu sub b is equal to E times, oh man, there's no margin for error here. E times h bar over 2 m sub E. And again, remember E is q sub E, the charge on the magnitude of the charge on the electron. And so then that's going to be 1.6 times 10 to the negative 19 coulombs. H bar is 1.055 times 10 to the negative 34 joule seconds. And this is going to be 2 times the mass of the electron, which is 9.11 times 10 to the negative 31 kilograms. And so when the smoke clears here, we get 9.274 times 10 to the negative 24 joules per Tesla. So we reconciled the units in class, and I wish that you do that again. So please reconcile the units for yourself. I'm not going to do it again. And again, the connector here is QVB sine of theta, as far as units are concerned. So that'll get you to where you need to go. So if we look at the angular momentum along the z direction, so if we're going to look at just the LZ component of the angular momentum, then what we have then is mu sub z is going to be equal to E. Oh man, going to be equal to E over 2 m sub E times L sub z. Okay. And so L sub z in magnitude, recalling from the hydrogen atom, is equal to m times h bar, m sub L times h bar. And so then mu sub z is going to be equal to E times h bar over 2 m sub e times m sub L. Oh, let me erase that. Times m sub, oops, here we go, times m sub L. We recognize that this needs to be negative. It's the charge on the electron, so that's negative. And so what we have here, this then is going to be the Bohr magneton. And so then we have that the z component of the angular momentum is going to be negative the Bohr magneton times m sub L. And that's worthy of a box as well. Okay. So now, what happens? The question is what happens? What happens if we place our system, and that system will be defined by some other context later. We place our system in an externally applied magnetic field. Okay, so the applied magnetic field will be along the positive z axis. So what happens? What happens now is we move from the classical picture to the quantum picture. And so we spent some time talking about this in class. So in the classical picture, right, mu can align perfectly with the magnetic field. Okay. But in the quantum picture, right, mu cannot perfectly align with the magnetic field. Why? So now I'm going to start to move into areas where I ask you guys more questions. And so we covered that in class. Give you a clue, it had to do with the Heisenberg uncertainty relation, but it is something that you probably ought to be able to describe to somebody, i.e. me. So, so now at this stage, if it can't, then what does it do? Well, what it does is, again, let's get this picture. Let's get this picture right. So, so here's mu. Right. So here's mu. Since we're talking about the electron, we know that mu and L are anti-parallel. So there's mu. There's L. Again, you should have this picture in your notes. We'll call this angle theta, and we're going to see that this mu is going to precess. It's going to precess about the z-axis. Now remember, the magnetic field is oriented along that direction, so we have b k caret along the z-axis. So we'll draw b vector as b magnitude k caret. So what happens in this case, and again, you might want to look up on YouTube. About the motion of a gyroscope. Motion of a gyroscope. And you'll see in that motion that you'll get this kind of precession that we talked about previously. So what will happen in this case is that the magnetic field will actually exert a torque on the magnetic moment, trying to align it. And so that torque is going to be equal to mu cross B, and that's a Halliday, Resnick, and Walker review, and so you should take a look at that. Please also note that there are many recipes for the torque, and we'll use two here, and I think we went over like 4 of them in lecture, so that should be in your notes, and I'm not going to review that here. Again, you could certainly review that in Halliday, Resnick, and Walker, but the torque is also equal to the change in the angular momentum with respect to time. Okay, so let's look at what happens down here with the angular momentum. So the angular momentum vector, right? So we have here. This is going to be. This will be. Oops, right here. This will be L sine of theta. Okay, again, if this is theta, then this is theta, and then looking at this right triangle here, then this distance here is going to be L times the sine of theta. We're going to call this angle in here d phi. Call this d phi. And then this arc length here will be dl vector. All right. So then the magnitude of the change in the angular momentum is going to be the magnitude of the torque times dt. And so this then is going to be mu b sine of theta from above, because if torque is equal to mu cross b, then the magnitude of the torque is going to be then the magnitude of mu times the magnitude of b times the sine of theta, okay, which we'll just let be equal to mu b sine of theta. So we know what mu is, then that's going to be, that'll be E. That will be E. That will be E over 2 emps of E times L B times sine of theta dt. And that's going to be equal to the magnitude of the change in the angular momentum. Okay. So looking at the change in the angular momentum from here, then we know that the change in the angular momentum in magnitude is going to be equal to L sine of theta d phi. It's going to be this distance here swept through this angle. Okay, so we equate those. We have L sine of theta d phi is going to be equal to E over 2 emps of E, the gyromagnetic ratio, times L B sine of theta dt. And so we get some cancellation here. And so sine of theta goes, L cancels, and we're left now dividing both sides by dt. We have d phi dt is going to be equal to E times B over 2 emps of E. Now, if you remember circular motion, right, so recalling circular motion, right, one knows that d phi dt can be written as the angular speed, or the angular frequency. Now that's a Halliday, Resnick, and Walker review if ever I saw one. So again, making the link between circular motion and oscillatory motion allows you to call omega either angular speed or angular frequency, depending on the context. Okay, so we'll use the angular frequency here. So this then is defined. Then we're going to define omega L to be d phi dt, which then is E B over 2 emps of E. And omega of L is called the Larmor frequency. The Larmor frequency. And again, we looked at the units in class. I want you, please, to reconcile the units rather. So please reconcile the units so that you understand the units, because you know that this must be, at the end of the day, this must be in radians per second. Beautiful. Okay. So let's end that third installment here, and then we'll pick up with some energy considerations in the next part 4. Wowzer, this is great.